Notes for research from inside NASA. From dream to discovery, waves and information transfer. Note: bolded words are defined further in the glossary. Space telescopes and probes have given us a window to the universe, allowing humanity to see the births and deaths of stars and to the very edge of known space. But getting that information back to Earth is a lot more complicated than you might think. Communicating in space. Communication with a spacecraft is essential for any mission, but especially those that are unmanned. Engineers on the ground need to monitor systems, send commands, and receive data. And to do so, they rely on waves from different parts of the electromagnetic spectrum. Because these waves are traveling through the vacuum of space, they all travel at the speed of light, the fastest speed at which information can be transmitted. Within the electromagnetic spectrum, radio waves are used for spacecraft communications. One of their most beneficial qualities is that radio waves can penetrate the Earth's atmosphere to reach communications equipment on the ground. They also require very little energy on the part of the spacecraft to produce. However, even with these characteristics, radio waves sent to and from a spacecraft can be very weak by the time they reach their destination, due to the large distances they must cover. To deal with this, radio dishes on Earth are often very large and able to be precisely pointed to collect as much of the signal as possible. Engineers are also making improvements to signal amplifiers and experimenting with higher frequencies to maximize the efficiency and quality of radio signals. Waves and information transfer continued. Map of the global distribution of the Deep Space Network facilities. Image CXC. The Deep Space Network is an array of giant radio antennas spread across the world, tasked with supporting and communicating with interplanetary space missions. The network consists of 3 facilities spaced approximately 120 degrees apart in longitude, located in Goldstone, California, Madrid, Spain, and Canberra, Australia. Their spacing is important because it means that no matter where a spacecraft is in the solar system, at least one facility has a line of sight to it at all times. As such, it is our primary method of communication with distant spacecraft inside NASA. From dream to discovery, page 6, waves and information transfer. Continued. Light speed and travel time. Beyond the strength of the signal, distance is important in communications because it means that spacecraft cannot receive instant commands to deal with problems or sudden emergencies. Even though radio waves travel at the speed of light, they still must cover such large distances that there are significant delays between when they are sent and when they are received. For example, for light to travel from the Sun to Earth takes about 8 minutes. That means the Sun is 8 light minutes away from Earth. Even further afield, Pluto is almost 4.5 light hours away. To deal with these delays, engineers have to program a series of commands for the spacecraft ahead of time. These commands are tested on a simulator in advance, reducing the risk for errors, at which point they are sent to the spacecraft. In some cases, engineers are left to wait for hours before they know if their commands were executed according to plan. This reflects the importance of patience and planning in modern space exploration. How a space telescope works. Pictures are some of the most common pieces of information sent back from spacecraft. However, what a telescope sees is not the same as what you might see in the eyepiece of a telescope here on Earth. In some ways, cameras on many telescopes and space probes are similar to the digital camera in your smartphone. Both use something called a charge-coupled device CCD, which collects light emitted by or reflected off objects. The CCD is a thin wafer of silicon divided into thousands, or even hundreds of thousands, of tiny light-sensitive squares. Each square corresponds to an individual pixel in the final image. And the more pixels you have, the more detailed the image. Squares on the CCD that line up with bright objects in the field of view will collect more photons, making those pixels appear brighter in the resulting image. This brightness is recorded on a grayscale ranging from 0 black to 255 white. So even though the final products we may see from telescopes like the Hubble Space Telescope could appear in stunning color, it is important to remember that the original images are recorded, essentially in black and white. To measure color, different filters can be placed in the light path of the telescope, with each filter designed to let through only certain wavelengths colors of light. By taking multiple images of the same object through a variety of filters, scientists can then combine the images to make a comprehensive color picture.